Can you hear me now? Yeah, so I was saying I'm Paul, I'm the founder of Sublier. It's a money streaming protocol. In my free time, I'm also like a Solidity math library developer, and I'm going to present this library called PRBMath. As you guys know, in Solidity, we don't have native support for fixed point arithmetic. So if you want to do things like logarithms, exponentials, and so on, you kind of have to do them from scratch, unless you're using a library. And we're going to talk about that today. The thing with like advanced math functions is that it's hard. You have to be both a good mathematician and a good computer scientist at the uni level. And the other problem is that very few math libraries in the wild use the latest v0.8 features, which I'm a huge proponent of. And I'm going to make this statement now. In philosophy, they like to say that everyone is a philosopher, even if you deny that you're a philosopher, that by itself is a philosophy. Well, in Solidity, because we like to use these very long numbers, right? Like 1 ether is 10 to the power of 18 way. Pretty much everyone is a mathematician in a very basic rudimentary way, and especially due to immutability. Like you have to ensure that your code runs correctly, and you have one shot to get it right. And I am lurking in this Ethereum Stack Exchange quite a lot. And this is one of the most common questions that I see. You know, how can I calculate the decimal value, right? You have, in normal human numbers, we have 1.4, 3.14, and so on. We just can't represent those numbers in Solidity. Well, you can, but you end up like doing this very ugly code snippet with many zeros, and it feels very, very ad hoc, like built on the spot, and you don't really think about all the implications of this when you write it up. So I did this for myself, and as I said, I was using version 8 of Solidity, and I didn't find anything that checked all of my requirements. So I created a solution for this called PRBMath. This was in 2021, so it has like 1 year since it's been up and running, and now it's used by various up-and-coming DeFi protocols. I think it has hundreds of users, more than 1,000 weekly downloads from NPM, from what I can see. So there's that. It is a modern math library operating with 18 decimal numbers, so it's instantly compatible with the Ether way representation. It has logarithms, exponentials, square roots, and more. It is gas efficient, but at the same time user-friendly. So we will go over some code snippets to see how that works. But I didn't compromise on gas efficiency. And it is well documented and commented. What I don't like about using an external library is that sometimes it reverts, and when you write a test, you need to account for those edge cases yourself. So I actually went ahead and commented every single line in my internal functions, such that if you ever bump into like an error caused by my library, you can go into my source code and understand the math rationale behind every step that I implemented myself effectively. So yeah, we have a very good developer experience. I have NatSpec comments everywhere. I like to say that if you yourself don't do the job of documenting your Solidity functions, nobody will. And complementary comments in function bodies and clear installation usage guides. And it's not just myself saying this. You have one of, I think he's working at Paradigm, so Frankie. Frankie is lost on Twitter, shilling PRBMath in action right there. So it's good documentation, and I'm not sure if you can see this, but on the left, that is the log2 function. As I said, every single step documented, and you can parse through the function itself. I'm using custom errors, and as far as I know, this is the first and only math library which uses custom errors at scale. I don't have any revert reason string. I'm a huge shiller of custom errors. If you don't use custom errors today, do that this evening. Like learn about them and do it, because they will save you gas, and you'll just you'll create a better developer experience for everyone internally and externally when other people read your code. And I'm using only custom errors. This is how they look, and it's very helpful to annotate the contract name, to put it in the prefix, such that if the contract reverts, people will be able to see where that error was coming from. Okay, testing and security, I have 1,400 test cases, 96% test coverage, and the remaining is actually code which is not used in production, and an audit coming later this year. And like use cases, by and large, percentages and proportionalities is the most useful one. So anytime you have something like 5% of this or that, PRBMath is the perfect library to use for that, because you don't have to think about all the implications of like rounding errors or like points and so on. You just have it ready to use. You have AMM applications, interest rates, derivatives, oracles, and custom trading algos. And here's basic example. Can you see it? Is it large enough? Okay, cool. What you do is just import the library like this. Then you use the using directive. You have two basic UI ints, and you calculate the percentage by multiplying by 100 and then divide it by that number. And I do want to say that this actually works with under the hood. I'm running this Maldiv operation, so you can have intermediary overflow. It can go to UI int 512 if the result goes to remains below 256. So it's very complex, very flexible, and it works with very large values. And another example, a more complex one, there is this AMM design called yield space. As you can see, it's pretty ugly in terms of like mathematics. I'm not going to explain that now. What I want to show is that you can do this kind of thing with PRBMath. And trust me, you do not want to go by yourself and implement this from scratch. I did. It was a long 3-month exercise for me. But you now, just look at this. Just a basic understanding of mathematics. And here you go. You have 4 lines of code which implement the complex formula on the other slide just by using PRBMath. So here we have the exponential function. You have the inverse function when you 1 over something, and some basic multiplication. But there we go. Complex math and Solidity made easy. And what is the future of PRBMath? Well, I'm moving to Foundry, so shout out to the Foundry team. I love it. I fully agree. Like testing in Solidity is the way to go. And once I do that, I will have fuzzing, so I will give you even more security guarantees. I also want to give a shout out to the user-defined value types, which have been implemented very recently in Solidity. Big fan. I actually started working on creating a bespoke type for my fixed point 18 decimal types, which will give even more security guarantees for you, because you'll be able to separate the PRBMath variables from the normal UI into your code. And in the future, hopefully, when Solidity will implement user-defined operators, I will be able to give you even like a better user experience. But that's it in terms of like futures. And this is like a sneak peek of that. Instead of having UI int 256, you'll provide this specific custom type that will only work with the PRBMath functions. And no gas overhead. So be on the watch out for this. You might want to even rewrite your code to use custom types in Solidity. So that was it. Thanks for coming. PRBMath is released under the unlicensed license, which means you can do whatever you want with it. Just don't sue me. And you can find me on Twitter and GitHub at Paul R. Berg. And if you want to see the GitHub, here's a QR code. And if you want to install it right now, you have npm the version with Yarn, or with Foundry, you can do forge install the repo name. Thank you.
So it's a really nice library, very big fan already, but I have a question regarding testing, like with these complex math functions, what's your approach towards that in a sense?
Yeah, it's a good question. So so far I've only been using Hardhat, so everything, the library has been written and designed and tested with Hardhat. I spent more time testing than writing the Solidity code, and you have 1,400 independent test cases. So that tells you something about how much I spent on this. But my approach was basically to go from the lower end, so the lowest inputs that can go into a function and the upper limits, test those, generate some random inputs around those values, and then provide 5 more like middle ground inputs, such that you test the entire function domain. And that was my approach. I actually have like 50 plus test files. So just test the entire function domain. That's it.
Okay, cool.
But no fuzzing yet. That will come later when I move to Foundry.
Hi, Paul. Thanks for the library. Two questions. One is, how do you deal with rounding? Because you mentioned you don't have to worry about that, but I think you do have to worry about that in some cases, right? And the second question is, what is the time complexity of some of these operations, like the square root?
So rounding is the same as ever in Solidity. Like Solidity rounds down. But if you use the PRBMath multiplication function, you actually gain a bit of precision because I'm using this very advanced algorithm for checking for 0.5 remainders, which are normally not accounted for in Solidity. So, sorry, the short answer is you have to be aware of how Solidity rounds down. You know, you have 3 over 2 will be 1. There will be no 1.5 in Solidity. You must be aware of that. But you don't have to be aware of the complex multiplication things where you have 3 terms and you know A times B over C. You don't have to think about the rounding there. You just have to be aware of the final result that it will not have 0.5 because Solidity rounds down. That's it. And then in terms of time complexity, it's actually quite, I'm biased, but I think it's quite efficient. If we go to, on the README, I have a gas table. And if you go to the square root, you can see that it goes from 114 at the lower end to 846 on the upper end. In fact, the most expensive operation PRBMath is the power function, which can go as expensive as 24,000 gas, which is still tolerable. So 24,000 gas is less than an ERC20 transfer. So there you go. Okay.
Hi, so maybe it's related to the previous question. I was wondering, is there any rationale or measurements of loss of precision with the different operations, like to understand, if I apply 4 of those operations, what am I getting with my numbers?
It's a very good question, and I do admit that for some very complex operations, I think for the X function, when you can have an arbitrary base, so the power function, when you can have an arbitrary fixed point base, and the exponential is an arbitrary fixed point type, that one will get you, I think, if I remember correctly from my tests, it's something like 12 decimals. So if you go to Wolfram Alpha, the website, they will give you precision, like unlimited precision. PRBMath gives you something like 12 decimals of precision, and afterwards it's kind of blurry. It kind of like loses its accuracy. It's a limitation of like not being able to have fixed point times in the first place in the language. But 12 decimals of precision, if your protocol uses 18 decimals in the normal case, it's still really good. So, but it's a good question. So there are some precision losses when you have complex operations, specifically power operations between fixed point bases and fixed point exponentials.
Thank you.